Let's talk about arguably one of the most insightful experiments in physics, conducted between 1908 and 1913, which completely changed how we think about the structure of the atom: Rutherford's gold foil experiment.
Ernest Rutherford, a physicist from New Zealand, was curious about what atoms actually look like on the inside. At the time, scientists were convinced in something called the plum pudding model, established by renowned physicist J.J. Thomson.
Basically, they thought atoms were just blobs of positive charge with electrons floating around inside, kind of like raisins in a pudding. However, this model failed to explain why the negative and positive charges were arranged in this specific manner. This model left too many questions unanswered. So Rutherford decided to test it, and what he discovered revolutionized the scene of science.
Now, before we explore the specific procedure, it's important to note that the entire apparatus was placed inside a vacuum chamber by pumping out air through a vacuum pump. This eliminated air particles, preventing interference with the alpha particles and allowing their trajectories to be clearly observed.
To begin, Rutherford used radium-226 as a source of alpha particles, which are positively charged and structurally identical to helium-4 nuclei. The radium was sealed in a lead box with a narrow slit, producing a thin directed beam to ensure accuracy and minimize random scattering of alpha particles.
Moving on, an ultra-thin sheet of gold foil, just a few atoms thick, was then mounted at the chamber's center. Gold was chosen for its exceptional malleability, which allowed most alpha particles to pass through. This setup enabled Rutherford to observe how the particles interacted with the atomic structure of the foil.
A circular phosphorescent screen coated with zinc sulfide surrounded the foil, so as the alpha particles passed or deflected off the gold foil, they struck the screen and produced brief flashes of light through scintillation. Scintillation refers to when particles transfer kinetic energy to zinc sulfide atoms, exciting them and then releasing photons upon returning to ground state.
A microscope was used to observe these faint flashes. The frequency and angles of deflections were also measured systematically, moving the microscope around the foil to detect particles scattered at various angles, including those that bounced nearly straight back. So what happened? According to the plum pudding model, those alpha particles should have passed right through, maybe with a few deflections. So, what did Rutherford see through the microscope?
Well, Rutherford observed a large number of alpha particles passing directly through the gold foil, like nothing was there. Whereas a few nudged off course and changed their direction at small angles. But the real surprise? A tiny number of alpha particles, about 1 in 8,000, deflected back to the general direction they came from, with some bouncing nearly straight back. These results told Rutherford something big. Atoms weren't just soft blobs of positive charge. Since most of the particles passed directly through, that meant atoms are mostly empty space. Additionally, the small number that got deflected back had to be hitting something solid, something positively charged, and for the very few particles that bounced nearly straight back, this indicated there must have been a highly dense center as well.
Thus, Rutherford called this positively charged center the nucleus, which contributes to most of an atom's mass due to the prominence of empty space. And for the electrons, Rutherford deduced that they must orbit this nucleus like planets orbiting the sun.
This was a profound discovery, changing everything we previously knew about the atomic structure. The plum pudding model was officially out, and the Rutherford model was in. Now that we've reached the conclusion of this scientific breakthrough, why do scientists even fuss so much over atomic models?
Well, for one, these models allow us to understand the behavior and properties of matter at an atomic level. Without these models, our understanding of matter itself would be severely limited. Without these models, we wouldn't have modern computing, LEDs, solar panels, medical imaging, and so much more. Rutherford's proposed model immediately inspired further investigation in pursuit of achieving a higher accurate representation of the atomic structure. It led to greater insights such as the identification of the proton and eventually the neutron. And so, Rutherford's atomic model is not entirely perfect. It was a scientific breakthrough that paved the way for scientists to unveil the true structure of atoms.